to be resynthesized to reconstruct the forwarding plan. However, the traditional configuration method has many shortcomings, such as slow update efficiency, poor performance, and handling limitation. This motivated us to develop a new configuration synthesis method. The part 2 presents motivation and case studies. Two challenges are focused on in this research. The first one is how to resynthesize network configuration efficiently, and the second is how to keep great network performance relies on resynthesized configurations to widely use routing protocols, so as the research background. There are OSPF and the BGP. The case one is an example of network merging when external routers 9 and 10 both have BGP announcement from network S3 at Zhaoyang table 1. If the local preference LP1 is greater than LP2, or when the route in S1 forward traffic to S3, the waypoint will change from external route 9 to 10. The change in the original forwarding path will violate the forwarding requirements and cause the security problems. The case 2 is an example of the impact of different configuration on network congestion. The OSPF ways marked in red and blue both meet the forwarding requirements but have different chains in the link load. In this example, the OSPF weight marked in blue will optimize the load of links 5 to 7, 4 to 5, and 1 to 4, which is what the synthetic configuration needed to achieve. The part 3 introduces the proposal NetRen. Firstly, we need to perform configuration sketch, instruction, and embedding. Based on the previous work, we used the special graph to model configuration sketch. The table 2 provides a summary of factor nodes divided into 3 categories. The network category includes a device, a routing session, connection, and the protocol includes link and routing announcement, and the forwarding specification includes forwarding requirements that need to be met, such as forward, reachable, and isolation. OSPF and BGP configuration parameters are provided in table 3 for input into the inference model. A set of learnable embedding function is built for different data types. In fact, they are linear layers. Network configuration synthesis is a very demanding task, and the synthesized configuration needs to meet all forwarding requirements. However, the neural network model cannot achieve 100% certification, so this objective is relaxed, and the configuration output by the inference model meet all forwarding requirements as much as possible. The inference model graph chains combines the graph model and the transformer model because the long-range attention of transformer model can solve the problem of big network size, and the decoder will output the value distribution of each configuration parameters. However, model synthesis configuration cannot be deployed directly, and they still need to be replied to ensure they are fully satisfactory. For this purpose, we provide a stepwise configuration repair. It's noting that the synthesizer provides a high quality configuration firstly, so it will increase the efficiency of repair and OO synthesis. The training of synthetic model requires sufficient data, so we provide the data generation process, randomly set configuration parameters in the network topology, compute the forwarding plan, and further extract a number of forwarding specifications. We consider the problem of network performance optimization, especially load balancing, mentioned in Chapter 2. Therefore, a traffic forwarding process is added to collect the changing link state, adjust the OSP weight based on the existing optimization algorithm, and collect data samples with optimized mapping relationship. Finally, we use the true value as the supervision signal and use negative log likelihood loss to train the model. This part is a report of the experimental result. The experimental setup is divided into 3 parts. The dataset includes the topology dataset and the training sample dataset. The model is structured by 8 layers of GCN and 8 layers of transformer encoder. The test platform is Omnight++. The experimental results are reported from the perspective of configuration, consistency, synthesis time, and link utilization, and a comprehensive comparison is made between the most advanced model GAT and the use of these 3 solo. This table shows the consistency result of the model's synthetic configuration. This is the configuration's certification rate for forwarding requirements, reach an average of 98%, compared with the 2% increase in GAT. The proportion of complete certification increased by 26.4%. Synthesis efficiency is important in terms of adaptability to network chains, and the proposal NetRen takes no more than a few seconds in all synthesis tests. Compared with JT, the efficiency of the synthetic model is improved by more than 7 times. Table 7 reports the acceleration factors of NetRen. Compared with SMT, the synthesis time is accelerated by more than 300 times. We have tested all topologies in top zone and conducted experiments with different number of forwarding requirements. We have advantage in both configuration quality and synthesis time. We compiled the NetRen synthetic configuration with the default and the random configurations for traffic forwarding testing, and found that link congestion is reduced by 5.83%. The picture below is a final OSPF and BGP configuration file output by NetRen that can be deployed. Finally, to summarize this work, in this work, a graph chain synthesizer is proposed that achieves end-to-end inference for synthesizing configuration, and performance optimization is introduced by constructing an optimization relationship in the data side. A network Renaissance framework NetRen is put out and achieves more than 300 times increase in synthesis efficiency and 5.83% improvement in network performance. And in the future work, we want to break through the constraints of modeling and realize network understanding and configuration updates directly based on the text configuration files. Thank you to everyone here, and I welcome your questions.
If you have any questions, I think if my right, so we'll move on to the next presentation. Akash Authority is a PhD student at UAC, advising Vighnesh Haifeng. His work has been primarily focused on automatically generating part compilers versus the productivity of compilers in the year, while providing formal strength. This is ongoing programming systems for domain and version memory technology. Hydride, Retargetable, Extensible systems, a compiler for modern hardware.
Do we need to do anything on my end to? Okay.
I should. Oh, this one's yours.
Oh, okay.
To cycle in. Yeah. Yeah, there it goes. Yeah, it just takes it a minute.
Okay. Thank you.
Yes.
Can I start? All right. Hi, everyone. Today I'll be talking about Hydride, a retargetable and extensible synthesis-based compiler for modern hardware architectures. Domain-specific language compilers today have custom backends to target different hardware architectures in order to maximize performance. Hydride, which is a DSL compiler for image processing and machine learning workloads, is no exception. In fact, its hexagon backend achieves about 2.6 times better performance than LLVM on matmul kernel, simple matmul kernel. But this approach to developing compilers has a number of limitations. It does not provide retargetability across ISAs. It requires arduously implementing pattern matching code for every single backend, pattern matching Hydride code to target specific code, and takes a lot of manual effort and time. And it is difficult to extend the backends or add new backends, especially for large, complex instruction sets. So we introduce Hydride, which takes us input pseudocode specifications to different hardware architectures, which are specified which are provided by the vendors, and formal semantics of Hydride to automatically generate code generation support to different hardware architectures. This is the first work to automatically design a target-independent instruction set for a retargetable compiler IR. It uses program synthesis and eliminates the need to implement pattern matching code, and also at the same time achieves comparable performance relative to the state of the art. And it minimizes the effort required to extend for new, large, complex ISAs. To just give you an example of what it looks like to support a new x86 instruction. First, you have to add a machine instruction to the LVM backend, and that machine instruction can be targeted using a target-specific intrinsic in LVM IR, which is not an unusual practice today. And that target-specific intrinsic can be generated from a target-independent LVMIR instruction. And what Hydride basically does is that it uses its automatic IR generator to parse the pseudocode specifications of different hardware architectures and develops an instruction set that is target independent and representative of the instructions of all the given ISAs. And it implements these target independent instructions as intrinsics in LVM automatically. And it also automatically generates the pattern matching code to pattern match target independent instructions to target specific ones. Hydride's code synthesizer takes halide IR as input and automatically synthesizes semantically equivalent target independent code, and it provides formal correctness guarantees since it uses the automatically generated target independent instruction semantics. And Hydride also supports other targets, including hexagon and ARM. And I'm just going to briefly talk about, just to give you a sense of what I mean by similar instructions. So let's look at the simple Intel VNI dot product instruction. It takes input vectors A and B, performs the dot product, and the result of that dot product is added to the source vector. And then HVX has a similar instruction for dot product. The difference is it operates on different register sizes and other instruction specific things. And what Hydride automatic IR generator does is it takes the pseudocode specifications of these instructions. And from it, it automatically generates an auto LVM IR instruction, which is a target independent instruction that is representative of both the Intel VNNI and HVX VRMPY instruction. It abstracts away all the instruction specific things like the vector size, the vector length, position, lane sizes, and so on and so forth. It gets more complicated with other instructions, but this is one of the simplest examples. And Hydride's code synthesizer also synthesize very complex data movement and compute instructions. And this slide just shows you an example of complex data interleaving pattern that Hydride is able to synthesize and also synthesize a widening dot product instruction for matmul kernel on x86. Whereas halide only manages to generate simple SIMD multiplication and addition instructions. And just by selecting a good sequence of instructions, Hydride is able to get 35% better performance than halide's x86 backend. Halide's backends for x86 and ARM are about 10 years old, and the HVX backend is about 8 years old. And these backends have been heavily engineered to produce really highly optimized code by teams at Google, Adobe, Qualcomm, and so on and so forth. Hydride was implemented from scratch for HVX and x86 initially. And in a little over a year, we managed to get comparable performance to halide. And then another student came along, worked part-time for about 3 months and supported over 1,200 instructions in that short period of time, easily with Hydride, just by providing pseudocode and parsing it, adding support for parsing it. And these are the performance results that you see, the speed ups relative to halide's ARM backend and halide's LLVM backend. And Hydride manages to get pretty comparable performance to relative to halide's ARM backend here. Now I'm going to briefly talk about auto LVM results. Hydride supports over 2,000 x86 instructions, And because x86 instructions each x86 instruction happens to have a lot of variants, the auto LVM IR instruction set is 15 times smaller than the original machine instruction set. And for HVX, we support over 300 instructions. And because HVX is small instruction set and has much fewer variants, we get about 2.7x reduction. And among all the targets that we support, we get about 9x reduction. Now I'm going to walk you through the performance tuning process using schedule-based DSLs and how sort of Hydride fits in the picture. So with DSLs like Halide, you first implement an algorithm. This is just a simple example of an algorithm for MATML. And then you implement schedules, which are basically loop transformations and a bunch of optimizations that you can perform. And Halide and DSLs like Halide just decouple this notion of schedules and algorithms. And when you compile this input program to Hydride, it synthesizes the code for it and caches the results of the synthesized code. And then you can compile and execute the program. Now, these are the compilation times for on HVX. We took benchmarks especially hand optimized for HVX. And the geometric mean of compilation times across 33 benchmarks that we evaluated, it's about 39 minutes using just synthesizing code through Hydride. And it's quite a lot. And this is not unusual. Program synthesis does take a lot of time, but this is just a one-time cost. In the rest of the performance tuning process, you just tweak schedules. You don't change the algorithm. And as a result of it, you can change the loop, you can perform a bunch of loop transformations, change the tiling factors and unroll factors and all the rest of it. But the core computation remains the same. And when you recompile this program through Hydride, Hydride just accesses its cache, retrieves the cache results, and any uncached results are synthesized, and then you can compile and execute. And then you can keep repeating this process. And this turns out to be not so expensive in terms of compilation times, as I'll show briefly. Compilation times, so this column shows the compilation times when your cache is fully warm, which is, these are the best compilation times you can achieve with Hydride. When the cache hit rate is 100%. And these are the compilation times after modifying the schedules in each iteration. And if you look at the geometric mean, it's roughly, it's pretty close. So the overall idea is when you're performance tuning with Hydride, you just pay the cost of synthesis once, and then you keep accessing the cache results for the most of the time. So in summary, Hydride is the first work to automatically design retargetable, target-independent IR instructions. It minimizes the engineering effort required to support the generation of new complex instructions. It maximizes instruction coverage since the whole approach is automated. And this is important for large ISAs. And it achieves comparable performance relative to the state of the art in the targets that we support. Thank you. I'm happy to take any questions.
Oh, I've got something offline.
Okay.
Hi, nice work. So I'm just wondering a little bit about, are you supporting ARM's SVE or Neon?
This is just Neon.
So can you comment a little bit upon supporting instruction sets with fundamentally incompatible or just different vector models, like like a vector within a word versus a dynamic vector length? like RISC-V style, or like, what do you think?
Yeah, that is much more difficult because the fundamental assumption is that you have to know what the vector length is. So I think at that point, I have to think more deeply about how you can support scalable vectors and even matrices, for example, Intel EMX. It's a tricky situation. But I think that is where, if there's more novel work to be done, I think that is a direction to go, I suppose. Yeah. Hi, AJ.
Hi. Extremely cool work. I just wanted to ask. So you report some speedups on the ARM backend over Halide, and I was just curious if you can give me any intuition, because there aren't really like any examples in the paper where those speedups come from, or if you have like any idea what like is Halide just missing, a pattern for a particular instruction or something like that.
The speedups that you notice are actually relatively small, and that is basically because of just selecting better data movement instructions.
Better what? Sorry.
Better data movement instructions, so the interleave instructions and stuff like that. But they're not a huge speed ups really across the board, really, if you look at the paper. Yeah.
Actually, I did have a question on this slide. What is the Halide LLVM backend?
So Halide LLVM backend is when you don't go through the ARM backend, but you just go through LLVM, just emit LLVM code.
Oh, so you would have had to modify the Halide compiler to do that.
Right.
Okay.
And just
Right.
form a bunch of LLVM.
Okay, so this is
optimizations.
before the target specific backends get a chance to look at it.
Right.
Okay, I was wondering if by LLVM backend you meant like the C backend that just generates C code and then pass that to.
Right. No, I don't.
Okay.
I don't
Yeah, I
mean
was
that.
just curious because the LLVM backend isn't really something that.
Right.
Speaking as a maintainer of the Halide language,
Yeah.
the LLVM backend is not something that we like expose to users per se. So when most of the time when we talk about the LLVM backend, it's one of the target specific backends that goes through LLVMs. That's what I was a little confused about, especially when reading the paper the first time. It's like 26%. Like we really need to do a lot better. But, yeah.
Right. Okay. Thank you. All right.
HDMI and audio.
The audio?
Our next
And the audio.
speaker,
Oh,
Kevin Laeufer.
there's no audio.
Tell me not to say his last name.
It's fine.
Anyway, he's a PhD candidate at the University of California, Berkeley. He works on the next generation of RTL scientific buffers for RTL covered interface for the Harvard languages and appropriately allocated RTL-Repair. He maintains the official GSOL testing library and is the author of the waveform parsing backend, the server waveform viewer. In the fall, he will start as a research associate at Cornell with Adrian Sanson. And today he's gonna introduce the word RTL-Repair, Symbolic repair, forward design code.
Yeah, thank you so much for the introduction, and thank you all for being here. So the scenario that we're thinking about here is that you have some sort of RTL design, like this little tiny counter in the bottom right, and there's some bug in it. Of course, in reality, we don't know what the bug is, but here we just introduced it, so we do know. It's that we set the overflow flag at 7 instead of 15. And so now we have this buggy counter, but really, like, believe me that we don't know what was wrong with it. So we run the test says something is wrong. But then we are left wondering or left working on debugging, like what exactly do we need to change to fix this counter circuit? And so, for a smaller circuit like this, it might not take hours, but it might take at least a couple of minutes to do so. And so wouldn't it be nice if we had some sort of digital assistant that would be like, hey, developer, do you want to like maybe try replacing this constant? Because I think it will fix your test bench. And so this is, I think, would be a really helpful thing to have. And this whole description that I provided you sounds a lot like automated repair. And so the problem statement that we're working with, the precise one, is that we're given an RTL design that is written in Verilog. And we're also provided with a test, or sort of something like a test in the terms of a failing input-output trace. What that means is you basically have a table that tells you for every cycle, these are the inputs we're applying to our design, and these are the expected outputs. And of course, we can only do a repair if some of the outputs of the design currently are not what we expect them to be. And then we want to find a change to the Verilog code automatically that will make this trace pass. And I added this restriction that I think it should be minimal, because essentially this will allow us to present the user with something that they can actually comprehend. And also, as we'll see, it makes it more likely that we'll actually do a correct repair. Now, there was a nice prior work 2 years ago at ASPLOS that basically inspired this follow-up work. And so the authors there, they provide us with this benchmark set of 32 different defects across 11 different designs. They propose an approach of repairing these, which essentially involves a genetic algorithm-based idea that uses some templates and some mutation and some crossover to come up with potential repairs, try them in a simulator, and then see if they work. Unfortunately, the repairs, they can take quite some time. So the fastest one is 8 seconds, but a lot of them take normally minutes or hours. And if we actually integrate it in this my idea where we're saying like, oh, I want to have this as really like an assistant, something that's somewhat interactive. If we're talking minutes or hours, this is not interactive. And you basically forget what you were debugging by the time you get the answer. Now, before I explain exactly what we are doing, let's look at one feature that was an inspiration that's from the prior work. So the prior work, it has these repair templates that basically are AST passes that look at the AST. So this is the Verilog AST, and they might try to like randomly identify some expression and then add a change. And so a change that the prior tool does is like it subtracts -1. And then because it's doing a concrete change to AST, it has to like serialize it, run it through the simulator, see what it does. Yeah, it could also randomly apply this change to any other part of the source code, assuming some restrictions. Now, what we are doing differently is we're doing symbolic repair templates instead of normal repair templates. And what this means is that we can express all possible changes in one AST pass. So basically, this is like our simplest repair template, and we have 3 of them in total. And so this repair template just goes ahead and looks at all the constants in your AST and replaces them with an expression like this. And so this expression essentially just says that a repair engine can choose to do a repair. So this phi is an indicator variable. Only if it's 1 do we actually do a change. Otherwise, we use the original expression. If we do a change, then we can, in this case, just generate any possible constant that will make this circuit pass. Okay. And so the way we can solve this is inspired by a standard bounded model checking approach. So if you do bounded model checking nowadays, what you do is you unroll your system for k cycles, and then you ask a lot of times an SMT solver if there exists inputs such that the system does something that violates an assertion. In our case, we actually do know all the inputs and we do know all the outputs because we're provided with this test bench trace. And so our repair query says, does there exist an assignment to the synthesis variables such that the inputs and output constraints of this test bench are abided by? And this is the basic repair query, which does not restrict the number of changes right now. But basically, we do want to like optimize for the number of changes, and this is how we express it with this indicator variable. So basically, we want to minimize the number of phis that are 1. And the way we do this, you could use a max SMT solver, but unfortunately, the SMT solvers that are specialized for solving bit vector theory for circuits don't implement max SMT. But we do not have a lot of like domain knowledge here that helps us to do an efficient search. And so the domain knowledge, number 1, is a lot of times the repair template does not actually yield a possible repair. So first of all, we just ask the solver to find any repair without restrictions. And if it says, yes, I have a repair, then it turns out that if a repair exists, a lot of time you can repair it in very few changes. And so that's why we just do a linear search starting at 1. So we ask the solver, hey, do you have a repair that only does 1 change? If it doesn't, then we say, oh, do you have a repair that has 2 changes? And then at some point, we normally end up with a repair. Well, we will always end up with a repair because we have the initial one. So in the worst case, we would like go back to that. So now that we have this algorithm, I just want to like present you how the whole system works. So the whole system is really end-to-end. We ingest Verilog, we produce Verilog. So we take the buggy design, we do a little bit of pre-processing just to make sure that we can actually turn the system into something that our formal tool can analyze. Then we have a repair template that we apply. Then we use the open source Yosis tool to generate a formal description. And then we just run our synthesis engine that essentially implements the algorithm that I just showed you. Now, if we don't have a repair, we just go to the next template. And we have 3 templates that cover all of our 40 or so benchmarks. And if we do get a repair, then we do check whether it's a large repair. If it has a lot of changes, then we try other templates. In the end, take the repair that does the fewest changes. If it is small already, we just immediately go ahead, patch the Verilog by just like plugging in the constants that the solver found, doing a little bit of constant prop to make the repair look nicer, and then we just emit the fixed design. Now, this is a real repair from the benchmark set that was provided by the prior work. You see basically changes two constants in this combinatorial circuit. Our replace literal template matches perfectly, undoes the change, perfect repair after less than a second. The prior tool also does a repair that passes the test bench. Unfortunately, it does so after 7 hours. And even more unfortunate, it turns out that it kind of destroys parts of the functionality of the circuit that's not tested. And this is my motivation, or one of my motivations, that I made our tool like guarantee that we find a minimal repair over our templates, because that means that if a line of code is never executed during a test, it will not be touched because it won't actually help you change anything or repair anything. Now we do have some scalability issues. That's always the problem. Like people are like, oh, you're doing formal, but then it won't scale to anything real. There's some truth to that, right? So like the problem is like basically as you unroll, you have more and more dependencies, your formula grows in size, and here's a little benchmark with like a bunch of the repairs that we're doing, and like really saying like, oh, how much do we unroll and how long does it take to generate a repair? And it goes up exponentially as we expect. But as it turns out, maybe we don't actually need to look at the complete test execution. So here's the test execution we have, and here we have this correct system. So this is our like ground truth. So we, of course, in a real scenario, we don't have that, but we assume we have a ground truth just to explain some things with. And then we have our buggy system, and we basically explain both of them. We execute both of them in lockstep with the exact same inputs. And then at some point, the outputs are different, and that's how we notice that there's a bug. This is our definition of a bug. The outputs are unexpected. And then, of course, the test bench continues executing, and at some point it's over. Now, how long are these test benches? Well, some of them are 11 cycles long, and then you can just unroll it all and just do the check as I explained in the beginning. But some of them are like one of them at least is 500,000 cycles. And there, if you start the SMT solver running, it won't return an answer before the universe ends. And so the first simplification that we can do is we can say, okay, what's the minimum number that we have of steps that we have to look at? And we have to at least include the first failure, because otherwise there's no failure and there's nothing to repair. So we could do that. There's one problem, that is that we don't include the constraints from the end of the test bench, and that means that we might get incorrect solutions. The way around this is we can actually sample multiple different repairs that are minimal, and then we can just try out all of them by running them on a concrete test bench. The other problem, though, is that like sometimes it actually fails after like quite some cycles, and so we still are unrolling too much. And so then the other insight is that, so the question is like, can we make the repair window smaller? And there the insight is that, well, if we start at the same state, for a lot of designs, the state actually evolves similarly between the buggy and the correct system. So this is our buggy design, where basically the overflow register is set incorrectly. But for the first 3 cycles of execution, the overflow register is still correct. Only when we actually activate this line is it updated to true, versus in the correct system it's updated to false. And so basically, in this case, we only need to look at this much of an unrolling. And so we can just concretely execute the system here, get to a concrete state, and then from that concrete state, do the symbolic unrolling. And so this way we can just focus on where the bug happens. And basically the way we do this, of course, in reality, we don't know exactly when the state will be diverging, but we basically just start with a small window and increment it if we can't find a good repair. And the problem is the other problem, though, is that like there might also be missing outputs in the future. So instead of just expanding into the past, we have a constant for how much we expand in the past, but also we can expand into the future. And so we just successively like make the window larger until we're at a point where we're saying like, oh, now it's taking too long, we just give up. And so this is an example of a repair that we repair like this. So this is a state machine that has like a state that's now aliased because of the bug that's introduced. The first output divergence happens at step 130. And then our tool basically starts with a window size of 0. It then says, oh, I need to include 2 steps into the future, then 2 steps into the past. And then with window size 4, it creates a correct repair within 3 seconds. And here basically it will replace the constant actually in 2 places, just because of the way that the replace literal template works. So for this simple example that we started with, it takes less than a second. So basically here, you just run the tool and then think instead of, like thinking about whether you should run the tool. And also in general, we have much faster repairs than the prior work. So instead of minutes or hours, we're doing it in mere seconds. We have much fewer wrong repairs, and the paper explains some details of why that is. And basically, we can sometimes actually say after 6 seconds that we cannot repair it because the SMT solver can actually say that there doesn't exist a repair, whereas in the other tool, timeout is the only way to know that you cannot repair it. Thank you very much, and I'm happy to take all of your questions now. Also, while people are queuing up, just a short thing, the paper has a lot of examples. So even if you feel like tired and don't want to read it, look at the figures if you just want to kind of see what's possible and what's not possible.
Yeah, nice work. So two-part question. So first one is if I had to think about something like a processor which has temporal state and I start running a program and it crashes somewhere, I don't know where. So what about systems that are temporal where I don't have a clear input state at which point the bug kind of happened? So how would I, like, any thoughts on that? Like this?
I mean, I think one of the points here is basically if you can narrow it down to like 20 or so cycles that you need to analyze, then it's fine. But of course, if you like don't actually know which cycle it happens in, then you're kind of lost. So basically for this processor thing, you would try to come up with some new domain specific heuristic of like how you narrow down that place, I would say.
Okay, and then the second question was so in the processor you have microarchitectural state and then programmer visible state in some sense, right? And so you don't typically have the bug might be in if it's in the visible part, it's actually quite easy to identify. But if somewhere within the pipeline, it's a lot harder. And so any thoughts on systems that have that kind of like split where there's visible versus just internal state?
Yeah, I think the answer here is that don't use this for hard bugs, use this for easy bugs. Like the whole point here is like, I think program repair, like the idea that it's gonna like take hours and then produce like this amazing repair of like this complex thing is just not gonna happen. But this is just showing that maybe it can be useful. You can make it fast enough that maybe it's useful for the stuff that you wouldn't even commit into a repository. You're just like, just extend the test bench and maybe it will suggest how to implement your next feature kind of, right? Like it's supposed to do the easy things fast. But it's not necessarily an answer for like super complex bugs.
Hi. So as I understood, you have like templates for different repairs you can do. So you have the replace a constant with another constant. You mentioned you have others. Which templates do you have?
Yeah. So they're actually like figures for each one in the paper.
Okay.
I just didn't include them here. So the one is called add guard. So essentially like it identifies like Boolean expressions that are sort of guarding things or somewhat akin to control expressions, and it can add like and another Boolean expression that it mines from the circuit, or up to 2 actually Boolean expressions. Conditional override is basically you say like, oh, there's a variable that's assigned in this process. I want to override it with a solver chosen constant under a condition that the solver synthesizes. And so those are like the patterns that like sort of are similar to like some of the bugs that we saw. So each one of these templates repairs at least 3 or 4 different bugs.
And one quick question, if there's time. You talk about Verilog, and then you show a bunch of chisel examples. Can you run this on chisel?
Right now, you can only run it on a chisel generated Verilog. I have a demo that does that, but yeah, on a generated language, it becomes harder. Like that's actually a place where like a standard non-generated language is much nicer to work with.
Cool.
Thank you.
Is also researcher at University. He obtained PhD at in three main areas of research.
Oh, no, I don't need so.
Static analysis.
Oh, but I need to insert it to my MacBook.
Generative AI, program analysis, and synthesis. This stuff he will present his work that will be which promotes the applicability of the license for different via code, programs. Ready?
Okay, great. Hello everyone, I'm Chenpeng Wang. I'm presenting our work serial, Empowering Version Compilability of Intermediate Representations while Program Synthesis. Intermediate representation is a middle-level representation of programs that bridges the source code and the binary code. During the past decades, the industrial and the academia has designed different IR codes, such as LLVM, JMPO, and CF code node, and there are many different theories behind them, such as CFG, SSA, and PDG. And such different kind of IRs have become fundamental materials for the program analysis, and different program analysis tools can be regarded as some kind of IR-based software, such as static analyzers, phasers, and symbolic tutors. Unfortunately, when the IR involves itself, it comes version compatibility issue. Specifically, the IR-based software, such as static analyzer, typically built on a specific IR versions. So if the program under analysis is upgraded and can only be compiled by the high version of compiler, we can only generate the high version IR code. But such version of IR code cannot be fed to the static analyzer anymore. So we refer this problem as IR version trap. So how to mitigate it? So there are typical two strategies, including upgrade the IR-based software to handle the high version of IR code as input. And also we can compile the program with low version of compiler to generate the low version IR code directly. But both these two strategies can only be conducted on the programs under analysis and a specific kind of IR-based software. So it not be generalized and leads to the significant manual labels for the developers of programs and the users of IR-based software. So in this work, we try to turn to another possible workaround. That is, automatically translates the IR between different versions, so that we can connect different ecosystems caused by the version incompatibility. So to motivate our design in the IR translation, we first conducted an empirical study about the ecosystem in the LLVM. And here are three typical sources of IR compatibility. Specifically, the major compatibility issue comes from the changes of IR test format, and also the APIs can change. And the minor issue comes from the new IR instructions in the new higher version of IR code. But this is only take a small proportion, just less than 15%. And also, we discovered very interesting finding that the IR formulation remains unchanged. That is, the grammar of the IR is almost fixed. Specifically, each function, program, and basic block has almost the same component across different versions. And also, an IR API supports us to extract and construct some IR code according to these IR APIs. So in this way, we found that we can utilize the IR APIs to achieve the IR translation and only need to focus on the instructions in the different IR versions. So based on such findings, we propose two important principles to achieve the IR translation. Specifically, we conduct in-memory IR translation, utilizing the IR APIs such as the reader, getter, builder, and writer to bridge two ecosystems of IR versions. For example, in this code, we show the entry function of IR translators for two different versions. Specifically, we first need to pass some element from the high version of IR and then translate it. And finally, we dump the low version of IR code to the disk. So what we need to do is just to synthesize the second part, which is the translate IR function. And for such translation algorithm, our second principle is to adopt the divide and conquer strategy for the hierarchical IR structure. So as I mentioned in our study, we found most of the structure in the IR code remain unchanged. So we can design the version agnostic skeleton that can translate all the IR construct except for the instruction. And for the instruction part, most of them are common across different versions. So in this case, we can adopt the program synthesis technique to achieve the automatic translation. Specifically, we can manually specify some test case to discover incorrect translator for different test case, for different instruction. And here is an example. If we focus on the branch instruction, we expect to synthesize such translator automatically. So as long as we can provide test case and enumerate all the instructions one by one and synthesize the translator for each of them, we can get the translator eventually. And for the rest of part, which are the new instructions in the new version, we can just hire some developers to manually implement the translator for them specifically, and it's totally acceptable due to their small proportion. So currently, our problem has become the test case guided program synthesis problem. The user provides a high version of IR as a test case that covers different instructions. And our synthesizer just to enumerate the candidate translators for different instructions, and it can just leverage the IR APIs to achieve this goal. By applying such candidate, we can translate the high version of IR to the low version, and by comparing their output, we can validate whether this candidate translator for each instruction are correct or not. So basically, this is a very standard workflow for the program test case guided program synthesis. But in our problem setting, we still need to face several challenges. Firstly, abundant IR APIs and subkinds of IR instructions pose a large search space. Even if we consider the branch instruction in this example, we actually need to consider two subkinds. And also, we need to select proper IR APIs to achieve this translation. And also, when we use the IR programs as test case, we cannot independently validate the correctness of the instruction translator because a single IR program always consists of multiple instructions. So how to do the fault localization during the synthesis process? So this is also a big problem. To address these challenges, we designed our algorithm Sarah and implement it as a system. Basically, Sarah takes the IR libraries and test cases as input. And it first generates the candidate instruction translators based on the type information so that we can get the well-typed program in the first step. And then we leverage the test case to do the refinement so that we can discover some incorrect translators for each instruction. So the remaining part, we can just use them to fill in our version agnostic skeleton as a result. So this is our basic idea. So now I will give more details about our technical design. In our first stage, what we want to do is to address a huge search space, and this is the key of achieving efficient synthesis process. So according to our observation, the IR APIs receive some kind of IR construct as its parameter and produce some kind of IR construct as return value. So we have such correlation or constraint about how to use the value produced by the IR APIs. Technically, we use such graph representation to show such relationship. So each reachable path in such IR type graph can induce a well-typed translator. And such translator can achieve the translation for given for specific instruction in the IR code. So this is a very traditional approach in the type-guided program synthesis. But now the problem is, this is a well-typed translator, but whether it can achieve the translation correctly. So in our next two steps, we try to validate the correctness of such a well-typed translator. But firstly, we still need to construct the translator for each test case. So in this case, we have subtraction and return instruction. And by prompt profiling such test case, we can obtain this information. And by composing the well-typed translator for each instruction together, we can get, for example, 6 per test translators for this test program. So in this way, we can bridge the instruction translator to the per test translator together. So next, we can just achieve the validation to find some incorrect translator for each instruction. So let's go back to this example again. Our synthesizer may identify these 2 translators for the subtraction. But actually, the second one is not correct because the return value of this case is 0. And even if we translate this subtraction to addition, the return value is still equal to 0. So such test case is not powerful to distinguish the incorrect one from the correct translator. But firstly, we can have other test case to help us discuss this case. For example, in the second program, if we apply the second translator to the subtraction, the return value is equal to 30. It's not equal to the oracle. So in this way, we can successfully identify such incorrect translator for the subtraction and just remain the correct one as a result. So this is our basic design in Sarah. And in the evaluation, we evaluate Sarah for 10 version pairs in the LLVM Iyer. And as shown in this figure, most of the instructions are common across different versions. And for the new instructions, we just ask some developers to achieve the translation and write the code manually. And for each pair, we can achieve the synthesis just 3 hours. So it shows the high efficiency of our approach. And we also quantify the efficiency of our, the benefit of our approach to the downstream program analysis client. Specifically, we show that our analysis can help the bug detection to discover almost the same number of the bugs if we analyze the code in the low version. And also for the fuzzing, we can reproduce 95% bugs in Magma benchmark, which is a widely used benchmark for the directed fuzzer. So as the last, I want to emphasize a very amazing result. That is, our approach can still benefit the system security because, for example, the Linux kernel is keeping evolving, but the latest version can only be compiled by the high version of IR code. But unfortunately, the existing static analyzer can only handle the low version of IR. So there is a gap between the system version and the static analysis technique. But our approach can fill this gap, and we can discover 80 new bugs, and most of them have been confirmed and fixed by developers. And some of them are even assigned with the CVE IDs, and this is just one of the examples. So for more details, you can refer to our paper. And at last, Sarah is just one of the important components of the static analysis platform developed by HKST. So for more details, you can scan this QR code for more information. And also we have another paper about the binary lifting we have presented yesterday. So this is also one important component of our big system. So welcome to know more details about our project. Thank you very much.
Let's thank our speaker again.
Okay, thank you.